Okay, so I will speak about consistent model selection criteria and goodness of fit test for common time series. This is joint work with Camilla Carré from my university, which is a PhD student, and William Kenge, which is assistant professor in Cergy in France. So this conference take place in the wonderful conference of modern statistics organized by Piotr, and I would like to thank a lot for this conference. So I will begin with an example for giving the framework of this work, of this talk. This first example is the observation of a trajectory of financial data, which are logarithmic returns of Standard & Poor's. And this is recorded from November 2011 till November 2016. So 5 years of closing values for logarithmic returns. And so the question we would like to study here is first to find an optimal model for modeling such time series. And our second aim will be to test the goodness of fit of this chosen model. Okay, so to be more precise, I will go back to very well-known definitions. The first one is the stationary property. So if we consider time series, which is a sequence of random variables on a same probability space, we will say that xt is a stationary process. Stationary here is the strict notion of stationarity. So it is a stationary process if you can have an invariance by translation of any finite dimensional vector of the process. So if for any k, any t1 and tk, the vector xt1, xtk has exactly the same distributions than xt1 plus h, xtk plus h for any h which is an integral number. Okay, so this is for stationarity. And the second definition we will use a lot here will be to define what is a white noise. And so a white noise is a centered sequence of IID random variable. And we will say that xt is a causal process if there exists a function h, which going from r power n to r, such as the xt is equal to h of the past of the white noise. This is why we said it is a causal process. It depends on the past of the white noise. Okay, so using both those definitions, we will provide two examples of time series which are well known. The first one will be the autoregressive processes, and more precisely autoregressive and moving average processes. I said here that this was introduced by Whittle in 51, but there will be already with Yule in the 20s the first definition of such processes. So if we consider white noise, we consider two families of the real numbers, EI and BG. We will say that XT is a ARMA PQ process if you have this relationship between the past values of XT and the past values of XT. Okay, so this is very well known, and I will not say all the conditions for this, because with such relationships you could also obtain ARIMA process, SARIMA process. So here I will just recall that when you have this condition, that is that 1 plus A1Z plus etc. plus AP ZP different of 0 for any Z in the unit disk, and then you have a stationary and causal ARMA process. Okay, so here I just recall a graph of a trajectory of an ARMA process. This is ARMA 11, and here the conditions are such that we are very close to non-stationarity. That is the roots of this polynomial here are very close to 1 in modulus. Okay, so you can see this the graph of this trajectory, and it's not really close to the one of our example. I just go back here. Not really the same, because we can see that here we are very centered here in such trajectory, but there are some very big fluctuations many times, but this is not such a case for ARMA processes. And in the beginning of the 80s, Engel and after him Boleslav proposed a new kind of time series, which is arch and after gauge processes. Here, gauge is the acronym of generalized, autoregressive, and conditionally heteroscedastic process. And such a new process were introduced for giving some model of such log returns I presented before. So even with still with a white noise XT, we consider two family of real numbers, CI and DG, and a gauge PQ process will be defined by these ways. You have XT, which is equal to sigma T XT, and sigma T is defined by recurrence relationships. Sigma T is volatility, and so the square of sigma T is equal to C0 plus C1, the square of XT minus 1, plus CP, the square of XT minus P, plus D1 sigma square T minus 1, plus DQ sigma square T minus Q. Okay, so we'll see here that the volatility is such a, which is an instantaneous variance, is depending of the past. That is that if previously, for the before t, you have very large values for xt, then there are more chance than xt as big fluctuation because you have xt which is equal to sigma t ct, and sigma t will be large here. But and so this is what we which is called the conditional heteroscedasticity. That is, you have the variance of the process knowing the past, which is not a constant. And when you consider ARMA process, you have not such a relation. You know, the conditional variance is a constant for any t. So now, with this kind of condition, which is not exactly a condition for strict stationarity, but a condition for second-order stationarity, you can say that the process is second-order stationary and causal. And here I gave also an example of a trajectory of a gauge 1-1. And we can see what we said before, that is, when you begin to be to have small values for xt, the time after you still have generally small values. And when you begin to have large values, for instance, here, you have more chance to have large values for xt. Okay, so this graph is really more, it's closer to the graph of log returns of Standard and Poor's we used as example. So now, with the recall of both these very famous kind of time series, we can say more precisely what we do now. We consider now a family of models, and for instance, our family could be all the ARMA PQ and all the gauge P prime Q prime processes with P and P prime less than P max. For instance, generally we use P max equal to 10, and Q and Q prime which is less than Q max, and as previously we generally use Q max equal to 10. Okay, so you have here a large family. For instance, here, if you count, you have 100 possible ARMA processes and 100 possible gauge processes. And if you use all those processes, we would like to find an optimal model in this family of model for modeling x1 to xn, which is the observed trajectory. For instance, the trajectory of log returns. After this, when we have obtained an optimal model for modeling, we would like to estimate its parameters. And finally, we will use this optimal model and its parameters for testing the goodness of this model. Okay. So this is what we're going to do now, but more generally for a larger class of models. And so this larger class of model is called the class of causal affine models. We go back to two more general example. We spoke before about ARMA processes, but ARMA processes could be generalized to AR infinite processes, which is defined by this way that instead of having finite linear combinations of past values, you could define xt as an infinite linear combination of the past value of xt. And you add just the white noise. And by this way, you could recover all the causal AMA PQ processes. But you could also define many of those stationary causal processes. So this is the first more general example of causal autoregressive processes. Another more general family of time series, which is a family of H-infinite processes, which have been introduced by Peter Robinson in 1991, and this is quite the same definition of some gauge processes, except that the square of the volatility is defined as an infinite linear combination of the square of xt, of the past value of xt. The gauge PQ processes are just an example, a particular case of arch infinite processes. So we have now two more general family of processes. And this will be a good way to introduce the new family of processes, which is causal affine processes, which is a common class of AR, AMA, arch, gauge, and maybe many other processes. So this class is defined in such a way: xt is a function of all the past value of xt times xt, where xt is still a strict white noise. And you add also a functional of all the past value of xt. So this is why we said that this is a causal affine, because you have causal because it depends only on the past value, and this is affine in terms with respect to the white noise. Okay, so with this definition, we have to say that ct is a white noise, but we assume also that there exists the R moment order for ct, and R is supposed to be greater or equal to 1. Okay, so just to have two examples of causal affine processes, we go back here to AR infinite processes, and we can see that xt is a functional of ct, but this functional is only a constant here, and you add the function f of the past value of xt, and here this functional f is infinite linear combination of the past value. And if we consider H infinite processes, here we can write this like sigma t times ct, and sigma t we can use a square root of phi 0 plus etc. The linear infinite linear combination of the past value of the square of xt. So for this second model, we have a functional f which is equal to 0, and the functional m which is exactly the square root of phi 0 plus this sum of square values of xt. Okay, so it is clear that R infinite processes and H infinite processes are particular cases of this general class of affine causal processes, which is called here. But we could add also many more processes. For instance, we can add the T-Garch or Tarch processes, which were defined by Jean-Michel Zakoyan, and which is a possibility which very close to Garch process, except that sigma t has not exactly the same behavior when the past value of xt are positive or negative. So you could use something like an asymmetric response following the values of xt. And the T here is acronym of result. Ding and Causers also introduced A-perch processes with another parameter, delta, which is supposed to be greater or equal to 1, and also P and Q. So the same kind of definition than the Garch processes with volatility, but the relationship is not between the square values, but the power delta values. And here you have also a possibility of non-symmetric response following the sign of xt. So this is for this family of processes. We can also make some combinations of the previous family of processes. For instance, we can define Arma-Garch processes. This is just to consider an Arma process, but the white nose here is replaced by a weak white nose, which is a Garch process. Okay, so this is just what is Arma-Garch process. And we can also define Arma-Aparch process with the same trick. That is, you have Arma processes, but the white nose is replaced by a weak white nose that is exactly an Aparch process. Okay, so now we can give very convenient condition for obtaining stationarity and causality for causal affine models. This condition will follow some Lipschitzian conditions of both the functional f and m. So if f and m satisfy Lipschitzian conditions, that is, when you consider x and y, which are some sequence of real numbers, you define the Lipschitzianity as the difference of fx and fy in absolute values should be less or equal to an infinite linear combination of x g minus yg, and in absolute values. And so this is a natural extension of the Lipschitzian condition for real numeric functional. And the sequence alpha g of f and here alpha g of m will be the smaller as possible. And when f and m are continuously differentiable function, both those family are equal to the partial derivatives of the supremum of the partial derivatives on R infinite. Okay, so now using this both those sequences alpha g of f and alpha g of m, we have a very useful condition ensuring the stationarity and the causality. That is, this condition is that the sum of alpha g of f plus the sum of alpha g n times the norm of the R norm of xc0 strictly less than 1. And by this way, you have also an ergodic solution, causal and ergodic solutions. Ergodic is satisfying large law of strong law of large numbers, and we have also R moment for x. Okay, so now using both those conditions, we can obtain directly condition of stationarity and causality for AR infinite processes, for H infinite processes, for T-Garch or Tarch infinite processes. Note that those conditions are not necessary and sufficient conditions. There are only sufficient conditions of stationarity and causality. Okay. The question now is how to estimate the parameters of such causal affine processes. This will be the first step before choosing an optimal model. We would like to know, to identify a model when we choose a model. So I will speak about Gaussian Quasi-Maximum Likelihood estimator for causal affine process. So we assume now that we have an observed trajectory of a causal affine process, but here we specify that the function m is depending on a parameter theta star, and the function f is also depending of theta star. Theta star is supposed to be in RD, so here we will consider parametric, or more precisely semi-parametric estimation of theta, because we will assume that m is known, but theta star is unknown. So the relationship between defining the dynamic of xt is the dynamic of a causal affine process. So you have, as before, the functional m theta star times xt and the functional f theta star of all the past value here. And now we will use some notation. We will say for any theta in RD, we will use the notation f theta t, which is f theta of the past value of xt, and m theta t is m theta of the past value of xt. Okay, using those notation, we can define the Gaussian conditional log density of the process. So for obtaining this, we will assume that ct is a standard Gaussian random variable. And we will use conditional log density, that is, we will give first the density of xt conditionally to the past value of xt. So by this way, this functional here, m theta of the path value is a constant, and this second path value, this second functional is also constant. So finally, conditionally to the path value, xt is an affine function of ct. So it is also a Gaussian process. So we can give its expectation, its variance, and finally, using the log density, we obtain the well-known formulas xt minus its expectation, which is now f theta t, square of this, divided by m theta t square, and plus the logarithm of the conditional variance, and times minus 1/2, because normally we have the logarithm of m theta t only, and here in the exponential you have minus 1/2. Okay, so now we have this conditional Gaussian conditional log density, and by this way we use some functional which are not exactly defined. Why? Because you see here f theta t is depending of all the path value of xt, but x0, x minus 1, and the other before are not observed. So we cannot obtain here a feasible density because f theta t and m theta t are not observed, could not be computed, could not be computed. So the way for using this Gaussian conditional log density is to replace the non-observed values x0, x minus 1, and others by 0. And by the way, we obtain an approximation of f theta t, which is called here f theta t, where all the path value before 0, which are replaced by 0. Okay, so there are other possibilities than to put zeros like this, but this is generally the most common and the most easy way for estimating m theta t. And now we obtain a pseudo Gaussian conditional log density here, which is at qt of theta, which is defined like this, where f theta t and m theta t are replaced by their estimation, as we explained before. And finally, now we can define a pseudo likelihood, log likelihood, conditional log likelihood, which is the sum of the qt of the at qt, and this expression for any theta could be computed from the observed trajectory, and now an estimator of theta will be obtained by maximizing this pseudo log likelihood, and it will be called the quasi-maximum likelihood estimator. And we could specify Gaussian, but because here everything was done using the assumption that CT is a Gaussian process, a Gaussian white noise, but now we will forget that CT is Gaussian. We can use this estimator even when CT is not Gaussian white noise. And so we can use this estimator and obtain some condition for the consistency and the asymptotic normality of this estimator. First, we assume that R is greater or equal to 2, and we will say that the second order is equal to 1 for not overfitting over parameterization condition. The second one, we will assume that for any theta, we have causality and stationarity with a moment equal to R, and here R will be equal to 2 for the beginning. After this, we will assume that m theta x equals greater or equal to m, and m is supposed to be a positive number. And this condition is really important for using quasi-maximum likelihood. With C3, we will have identifiability condition, that is when you have m theta 1 equal to m theta 2 and f theta 1 equal f theta 2, then we should obtain theta 1 equal to theta 2. And finally, we have other condition on the functional key theta. Here key will be replaced by m or f, but also by the derivatives of m and f. And this condition is the same kind of conditions and Lipschitzian condition we provided for f and m. And here we assume that the sum of the Lipschitzian coefficients is the finite sum. So using those condition and notation, we will obtain the strong consistency of at theta of the quasi-maximum likelihood estimator to theta star. And the condition is the following: if you assume that R is greater or equal to 2 and both all the other conditions, and also that the decreasing rate of Lipschitzian coefficients are not too slow. That is, we would like that it decreases as g power minus L, where L is greater than the minimum of 1 and 3 divided by R. Okay, so for instance, for R equal to 2, we obtain that L is greater than 3 over 2R. Sorry, here it should be a maximum and not a minimum. And when R is greater than 3, then you just have a condition here with G power minus L and L greater than 1. Now we will use also those notation and condition for obtaining the asymptotic normality of the estimator, and this is what we have obtained with Olivier Vantenberger. So under the previous condition, and now if we assume that R is greater or equal to 4, and if we have some stationary causality condition with R equal to 4, and if we also have some Lipschitzian conditions for the F and f theta and m theta, but also the first derivatives and also the second derivatives of both those functions. And if the decreasing rate of the Lipschitzian coefficient for the derivatives of f theta and m theta is not too slow as previously, then we obtain that theta n is asymptotically normal. That is exactly, we have this central limit theorem, square root of n times theta n minus theta h star, converging in distribution to a normal law where there are here two asymptotic covariance functions. G is the expectation of square of the derivatives of first derivatives of Q, and F is the expectation of the second derivatives of Q. So all these theorems, this asymptotic normality and strong consistency, could be applied to ARMA, to ARCH, to APARCH processes. Why? Because in such a case, we have the Lipschitzian conditions, and the decreasing rate is an exponential rate. That is, it decreases exponentially fast. So no problem for using those theorems in all these cases. It requires that R is greater or equal to 4, and it's not a very robust way of estimating the parameters, and there are other solutions for obtaining, for instance, R greater or equal to 2. But I will not say more about this. Okay, so now I'm going to the problem of selecting a model. And by this way, we will use a penalized quasi-maximum likelihood criterion. And using this also, we will obtain a Portmanteau goodness of fit test. So the first thing we could say is that because we have a causal affine time series, if we have two models of causal affine time series, it could be explained, it could be written as when you consider the union of both those models, it could be also explained, also written as a causal affine model. But here you use a new parameter theta. It could be, for instance, the concatenation of theta 1 and theta 2, which are the parameters of both the causal affine model. This is really linked to the affine property and inner property. And it will be very useful because when you use any finite family of finite dimensional family of causal affine process, you can find a common model where all the different model could be written with. That is, it is developed here. This family with different process, different parameters and different model and different functional M and F could be written in this common framework. That is only one way of writing M and one way for writing F, and one common parameter theta in any case. That to be more precise, for instance, we can write all the ARMA PQ process using the ARMA Pmax and Qmax process. For instance, ARMA 1,1 could be expressed as a particular case of ARMA Pmax and Qmax. This is exactly what we say. But this property could be also written when you mixed ARMA and gauge processes. You can have a common model, which is an affine model, causal affine model, for writing all ARMA and all gauge process. Okay, so now finally, because any model of this family could be expressed with the same theta, the difference will be the difference between the model will be the difference of coordinate of theta which are or are not equal to 0. And so we could replace any family of models by a family of set of the set 1 to D, if we assume here that theta is a vector of Rd. And so, for instance, if we consider a family of ARMA processes where P and Q are less or equal to 10, you can consider ARMA 2-2 process as the condition the theta will be A1 to A10 and B1 to B10, and when you have ARMA 2-2, you will have all A3 to A10 and B3 to B10, which are equal to 0, because this is ARMA 2-2 and no more. Okay, so you could identify a model with the non-vanished coordinate of the model. Yeah. So now we have an observed trajectory x1 to xn, and for n which corresponds to a model of time series of including in the family of models M, we could define the estimator of theta, and we could also define an estimation of an optimal model, which is exactly -2 times the quasi-maximum likelihood plus penalty here, which is depending on the dimensional of the model, which is for instance the number of estimated parameters, which is m, the cardinal of m here, times kappa n, where kappa n is an increasing sequence of positive real numbers. And we will specify what should be kappa n. So this definition is not really surprising or new. It's very close to what is known as EIC criterion or BIC criterion. except that for AIC, kappa n is a constant equal to 2, and for BIC, kappa n is equal to the logarithm of n. So this is just a generalization of both those well-known criterion of model selection. Okay, so using this criterion, we could recognize the true models when there exists a true model. So assume that you have an observed trajectory of m theta star and f theta star, and you assume that theta star, and so m theta star, f theta star, is in the family of model. And assume that R is greater or equal to 4, and previous assumptions on the asymptotic normality we have done before. Now we add another condition. This condition linking the sequence kappa, here kappa k, to the decreasing rates of the Lipschitzian coefficient of f, of m, and first derivative of f and first derivative of fm. So if kappa is greater enough for this sum is finite, then the selected model is asymptotically consistent. That is, we recognize the true model asymptotically. Okay, so this condition are not so difficult to obtain. This condition for kappa is not so difficult to obtain. For instance, if you use ARMA, Garch, Apache processes in your family of models, you have an exponential decreasing of those coefficients. And by the way, you just, the only condition which is required for the consistency is that kappa n going to infinity. And so, for instance, the BIC criterion is sufficient. That is, if you consider kappa n equal to logarithm of n, you could recognize the full model in the family of models. Okay, but if the decreasing rate is not exponential, and for instance could be written as g power minus gamma, now you could not select what you would like for kappa n. And for instance, here you should have something like n power delta, and delta is greater to 2 minus gamma. So for such processes, there are some family of processes, for instance, for AR infinite or H infinite, for which the BIC criterion is not sufficient for obtaining our consistency. I just would like to say that this is a sufficient condition. This is not a sufficient necessary condition. So perhaps it could be consistent BIC, but not using our conditions. Okay, so finally, if we use now the chosen model, the selected model at M, we can estimate the parameters of this selected model, and asymptotically, we have exactly the same asymptotic normality than we have before. That is, to know or not, to work on the full model or on the optimal selected model, asymptotically, there will be no difference. We could also obtain the same central limit theorem. So we lose nothing without the knowledge of the model. Finally, we will speak about Portmanteau goodness of fit. So it's something now very classical for instance, for testing if time series is a white noise. It was developed by Box and Pierce, and after by Jung and Box. And so the way we will test the goodness of fit will be to consider the residuals of our time series. Now, we have selected a model. This is at M. We could estimate the model, estimate the parameters of this selected model. This is at theta. And using the definition of the optimal selected model, we have normally we have xk, which is m times xi plus f. So using these relationships, we could define xima k at xima k, which is an approximation, an estimation of xi k, their residuals. And now, using those residuals, we can, the idea of this goodness of fit will be to test if those residuals are really a white noise or are close, sufficiently close to a white noise. And for this, we will not directly work on the residual, but on the square of residual. Because if the model, the selected model is a good model for observed data, normally we should have a white noise. The square of residual should be close to be a white noise. So for this, we consider covariagram of square residuals, and more it will be more interesting to consider the corollagram of square residuals, which is the ratios between the covariagram for lag k and for lag 0. Okay, so using those corollograms, we will define, we will obtain central limit theorems with also another condition on xi, which is that the power 3 of xi is equal to 0. And so by this way now, the corollagram of lag 1 to corollagram to lag k is converging in distribution to a normal law, Gaussian law, with here asymptotic covariance v of theta star, which could be detailed. We can give its expression here. I do not give it because it's a very long expression, but it depends on functional f and functional m and its derivatives. So it is asymptotic covariance that could be approximate. And so now, using such kind of approximation and using a norm, usual norm of this vector here, we obtain a chi-square limit distribution for this norm here. And this statistics, QK, will be the test statistic, the goodness of fit test statistic, a Portmanteau test statistic for testing if there is X, the observed trajectory is really an affine causal model or not, and an affine causal model which is included in the family of considered affine causal model. Okay. I am going to finish by numerical results, Monte Carlo experiments. So we have done many simulations, and in many cases, for instance, we will generate an observed trajectory that will be an AR2 process with these relationships, and now we will try to recognize this model in the family of ARMA processes, only ARMA processes, but with ARMA which are with P and Q less than 10. And for instance, for this model, we can see that for n equal to 100, T is for true. We recognize 74% times when we use BIC criterion. If we replace log n by square root of n, it will be only 67% times. And finally, using slope heuristic here, we could improve our criterion, and we obtained 79 times percent times the true models. When we increase n, we're going from 100 to 500 to 1000 to 2000. For instance, here you can see that we always recognize the true model. W is for a wrong model, and O is for overfitting models. That is a larger model than the real one, so than the true one. So here we can see that finally only the BIC criterion overfit is possible, could overfit. Above the other one do not overfit. Now we can also do the same thing when the generated trajectory is an ARMA 1-1, and now we still use the family of ARMA processes, and here the results are very good as after, for instance, perhaps for n equal to 500, we generally recognized the true model. Now, if we use arch processes, and now we will use a family of ARMA and arch processes and gauge processes. So we have a very large family of processes. The results are not so good. You can see that, for instance, using kappa n equal to square root of n, we have not really good result, and many times we find a wrong model, not an overfitted model, but a wrong model. But finally, when n equal to 2000, 95% times we find, using a BIC, we find the true model. And this is the same using slope heuristic. Okay, so this is first simulations. We can use those models to test the size and the power of the goodness of fit test we developed. And here we can find that for k equal to 3 or for k equal to 6, generally, when we choose 5% for the error of the goodness of fit, we are very close to this size, except for arch processes where we have not so good when n increase. And for the power, we use a false model, which is ARMA 1, 2, and we compare. We see how many times this model is not chosen for modelized AR2 or ARMA 1, 1 or AH2. Obviously, it is more. It is easier to not accept ARMA 1, 2 when the observed trajectory is an arch process than when it is an ARMA 1, 1 or AR2. Okay, so perhaps I will let this, and I will go back to our first example for the log return of standard proofs during 5 years, and using kappa n equal to log n, or kappa n equal to square root of n, or kappa n equal to what is given by the slope heuristic, we always find as an optimal model the Garch 1-1 model. And if we use our goodness of fit test, we find it accepts this model with a p-value equal to 0.5. So finally, it is what is commonly accepted. Garch 1-1 is a good model for the log returns of most common standard proofs. Here, sorry, I do not know what is this FTSE. Normally, it is standard proofs. Okay, this is the end of this talk. I'm just going to the references, and this talk was the consequence of a paper which is published in Electronic Journal of Statistics, and you can see here all the most interesting and most related paper to this talk. Okay, so thanks a lot.